Good evening, Farah. Good evening, Amit, Amruta, Pooja.
Good evening, sir.
Good evening, sir.
So today
evening,
we
sir.
will learn about the normal probability curve. No? Farah?
Yes, sir. It is the second module. The second part.
Second part. Whether the
Hello.
hello, Amrit.
Yes, sir. Actually, my request is to Farah. Farah, can you send the link on Gmail? Because actually, I am outside Raipur and I am having a problem with Wi-Fi here. Can you send the link on
Okay.
Gmail?
Okay. Yeah, I'm sending you. Okay. One.
Yeah, thank you.
Good evening, Shara.
Good evening, sir.
Is it visible to all of you? No. Is it visible to all of you?
Yes, sir.
Yes, sir.
Okay, so one can read. Please start reading. Pooja, please start.
Yes, sir. The normal probability curve, also known as the normal distribution, is one of the most important concepts in statistics and probability theory. There are several reasons why we study the normal probability curve. Common distribution. Many natural phenomena and statistical data sets exhibit a normal distribution. Therefore, understanding the properties of the normal distribution allows us to analyze and make predictions about a wide range of phenomena. Central limit theorem. The normal distribution plays a central role in the central limit theorem, which states that the sum or average of a large number of independent and identically distributed random variables tends to follow a normal distribution, regardless of the underlying distribution of the individual variables.
Is it clear to all of you? Hello, Pooja. This is clear. Large number of independent and identically distributed random variables tends to follow a normal distribution. Is it clear to all of you? So if we apply the histogram based upon the random data using the rnorm command, okay, we will find the majority of the data are clustered at the middle point. Okay, so that is the central limit theorem. Is it clear to all of you?
Yes, sir.
Okay. Next.
Statistical inference. The normal distribution is used extensively in statistical inference, which involves making predictions or drawing conclusions about a population based on a sample of data. Many statistical tests, such as the t-test and ANOVA, assume that the data are normally distributed.
Okay, so is it clear? That is why we use the normal distribution for statistical inference. There are several parametric statistics, right? Like the t-test, ANOVA. They are following the assumption of normal probability curve. Therefore, if your data does not have the normal distribution characteristics, then your inference will be biased. Okay. For that reason, we have to pay much attention to the sampling distribution so that we can tell, okay, we have done the t-test, we have done the ANOVA, and that is appropriate. Next.
Descriptive statistics. The normal distribution is often used as a benchmark for describing other distributions. For example, we can use measures such as skewness and kurtosis to compare the shape of a distribution to that of a normal distribution.
Okay. So we have to study whether the sampling distribution follows the normal distribution properties or not. If it is skewed, then we have to rethink. We have to redesign our sampling distribution. Next.
Overall, studying the normal probability curve allows us to better understand the behavior of random variables, make predictions about real-world phenomena, and perform statistical analysis on data. History. The normal probability distribution was introduced by the French mathematician Abraham de Moivre in 1733. He used it to approximate probabilities associated with binomial random variables when n is large. This was later extended by Laplace to the so-called CLT, which is one of the most important results in probability. Carl Friedrich Gauss in 1809 used the normal distribution to solve the important statistical problem of combining observations. Because Gauss played such a prominent role in determining the usefulness of the normal probability distribution, the normal probability distribution is often called the Gaussian distribution. Gauss and Laplace noticed that measurement errors tend to follow a bell-shaped curve, a normal probability distribution.
Now read center
So
limit.
there is a yes, sir. So before that, in the first paragraph of history, there is a CLT something. So what is the full form of that? Before that,
Carl Friedrich Gauss.
some theory in statistics. CLT, yes. Most important results in probability. So is this a central limit theorem? Okay.
Center limit.
Okay. The central limit theorem. The central limit theorem is a fundamental concept in statistics that describes the behavior of the means of a large number of independent and identically distributed random variables. In simple terms, the central limit theorem states that as the sample size of a random variable increases, the distribution of the sample means will approach a normal distribution, regardless of the underlying distribution of the original variable. For example, let's say we have a population of people with different heights. If we take a random sample of 100 people and calculate the mean height, it may not necessarily follow a normal distribution. However, as we continue to take more and more samples of 100 people, the distribution of the sample means will start to look more and more like a normal distribution. The central limit theorem is important because it allows to make inferences about a population based upon a sample, even if we don't know the underlying distribution of the population. It is used extensively in statistical inference, hypothesis testing, and confidence interval estimation.
Okay, is it clear? CLT? Okay, next.
Measurement error in normal curve. Measurement error refers to the discrepancy between the true value of a variable and the value that is measured or observed. In the context of a normal probability curve, measurement error can be visualized as a difference between the true score of a subject on a continuous variable, such as height, weight, or IQ, and the score that is recorded due to imperfect measurement instruments or methods. Measurement error can have several sources, such as limitations in the precision of measurement instruments or differences in the interpretation of instructions or questions, and variability in the conditions under which measurements are taken. These sources can contribute to random error, which is a type of measurement error that affects individual observations and causes them to deviate from the true score in a random manner. The errors are normally distributed with a mean of 0 and a certain standard deviation. The normal probability curve is symmetric and bell-shaped, with most errors clustering around the mean and fewer errors occurring at the tails of the distribution.
Is it clear? Measurement error? Hello?
Yes, sir.
Students? Okay.
Yes, sir.
Characteristics.
One second.
First, symmetry. The curve is symmetric about its mean, which is also its peak. If we were to take a large number of samples from the population and plot the values of these samples on a graph, we would find the majority of the values cluster around the mean. Peak location. The peak is found at the location of the mean. As we move away from the mean, the probability density of the curve decreases, resulting in a lower likelihood of observing values further away from the mean. Unimodality. It indicates that the majority of observation or measurement in the population or sample are clustered around the mean, with fewer observations occurring in values further away from the mean. Bell-shaped. The curve is bell-shaped, with the tails asymptotically approaching the x-axis as they extend further from the mean. The bell shape of the normal probability curve is a result of the central limit theorem. It states that the sum or average of a large number of independent and identically distributed random variables approaches in a normal distribution, regardless of the underlying distribution of individual variables. This means that many real-world phenomena, such as human height or IQ, can be modeled as normal distributions because they are the result of multiple independent factors that contribute additively to the final outcome. Asymptotic. The curve approaches but never touches the x-axis as it extends to infinity in both directions. Area under the curve. The total area under the curve is equal to 1, meaning that the probability in any possible event occurring is 1. Central tendency. Location of central tendency is at the middle point of the curve, and it is 0. Standard deviation. The standard deviation is a measure of how much the data deviates from the mean or average. In a normal distribution, about 68% of the data falls within one standard deviation of the mean. About 95% of the data falls within 2 standard deviations of the mean, and about 99.7% of the data falls within 3 standard deviations of the mean. This is known as the empirical rule, or the 68, 95, 99.7 rule. Skewness. Skewness is a measure of symmetry of the probability distribution. In a normal probability curve, the distribution is symmetric, meaning that it is equally likely to have values that are above or below the mean. And the curve is centered around the mean. Therefore, the skewness of a normal probability curve is 0. Quartile. In a normal distribution, the first quartile is located at a z-score of minus 0.67. The second quartile, which is the median, is located at a z-score of 0. And the third quartile is located at a z-score of 0.67.
So this is the area of the normal probability distribution. Please, you do not forget, which is the area. Can anybody tell me why it is 68.26%? What does it mean?
Sir, it located between the plus 1 sigma to minus 1 sigma.
And the total population will be 68.26%, right? Or 68.26%. Because
yes, sir.
Both sides, mean plus minus standard deviation is there. Yes, and 34.13, another one 34.13. Okay. Pooja অনেকক্ষণ পড়েছে. Sorry, in Bengali.
Yes, I understood, sir. So, I have few friends from the speak Bengali.
Okay.
Applications.
So,
Yes.
Pooja, now you know, maybe Shima, whether Shima has joined. Hello, Shima, are you
Yes,
here?
sir.
So please you read.
Good evening, sir. Yes, sir.
Please you read applications.
Yes, sir. Applications. The normal probability curve and its characteristics have numerous practical uses in various fields, some of which are statistical inference. The normal distribution is widely used in statistical inference, such as hypothesis testing and confidence interval estimation. It is used to model the sampling distribution of many statistics, such as the mean and standard deviation. Quality control. The normal distribution is used in quality control to identify defects in products and processes. It is used to model the distribution of measurement and to set tolerance limits. Financial analysis. The normal distribution is used in finance to model the distribution of stock returns and to calculate probability of future stock prices. Medical research. The normal distribution is used in medical research to model the distribution of many physiological measurements such as blood pressure, heart rate, and body temperature. In 2016, Niramai Health Analytics from Bangalore, India developed a non-invasive, low-cost solution to screen early breast cancer based on mapping body heat embedded with artificial intelligence technique. The patient profile was seen to be normally distributed as innovators 2.5%, early adopters 13.5%, early majority 34%, late majority 34%, and laggards 16%. Educational testing. The normal distribution is used in educational testing to model the distribution of test scores and to set grading curves. Psychometrics. The normal distribution is used in psychometrics to model the distribution of psychological traits and to set cutoff score for psychological test. Risk analysis. The normal distribution is used in risk analysis to model the distribution of losses and to calculate probabilities of extreme events such as natural disaster and financial crisis. Estimation.
Very good. 1 second. Now, who can read more? Shara, are you here?
Yes, ma'am.
Okay, so please you read. Estimation.
Estimation, point number 1, statistical inference. The hypothetical data set. Let's say we want to test the hypothesis that the mean height of a certain population is equal to 170 centimeter using a sample of 50 individuals. We will use a significance level of 0.05. Here's the data. The data set, height, C parenthesis, 169, 172. Sir, should I read all the numbers?
No. Number not required.
Okay, so in the heights, we created a variable for a vector for heights in which we included the 50 individuals data, and this is the coding as we can see. The sample mean is 170.1 centimeter and the sample standard deviation is 1.22 centimeter. To test the hypothesis, we will use a one sample t-test. We can calculate the test statistic and the p-value as follows. Again, there is coding for the same. The test statistic is 1.45 and the p-value is 0.154. Since the p-value is greater than a significance level of 0.45, we fail to reject the null hypothesis and conclude that there is not enough evidence to suggest that the population mean height is different from 170 centimeters. Next, we can calculate a 95% confidence interval for the population mean height using the t-distribution. Again, we have the coding, margin error, lower CI and upper CI. The 95% confidence interval is 169.67, 170.53 centimeter. This means that we are 95% confident that the true population mean height falls within this interval.
Is it clear now why we study the confidence interval?
No, sir, I did not understand.
How much confidence you can assign to your data? Okay, so that is revealed through this confidence interval. That is true population mean, where it lies. That can be understood through the confidence interval. The quality control is not required for your purpose. I don't want to discuss this quality control. Financial analysis not required. And that is the, oh, so this is the normal distribution, and you can find out that true mean lies here. And it is the confidence interval. The formula is this. You can apply the R norm. Okay. Now you go to the RStudio. Pooja, can you go to the RStudio? Do you have
Yes.
the RStudio? Yeah.
Yes, sir.
Okay, now I am writing the formula, sorry, the script, and you write this script on your laptop, on your RStudio. Okay. Is it clear to all of you? The R script that I have written? So yes. Now you select all of them. Select all of them and Control A, yeah. Then run. Okay.
Sir, we have to write this.
Yeah, definitely. Please do follow. Last time you have understood the R norm. Can you remember R norm?
Yes, sir.
So in case of the R norm, first value, that is the number of sample. Okay, sample size. Second value is the mean. Third value is the standard deviation. Okay, and that is the sample data. So Pooja, you can write down only the HIST, H-I-S-T, HIST. In brackets, sample data. Then run.
Sample data is, I think I should put this underscore.
Yeah,
Then-
definitely. Okay. So this is the distribution. Is it clear? Okay. Now you write down in the console, you write sample mean. Enter.
10.068.
Okay. 10.07. And you look at the histogram. There again, you will find that is the mean. The data lies here. Okay. Okay, now you write the next one, sample SD. Enter.
1.85.
1.85. Okay, because we have written the SD is 2. So it maintains that one. Whatever the command you have given, it follows it. Next, you write down conf int. Conf int. Okay, so that is the confidence interval. Next is the cat, the 95. So you have to copy that one and you can put. It's not possible. Just to copy that line. Only this line. Yeah. Paste. So what is the advantage of cat writing? It writes the output, okay, as you want.
Okay.
Here you can find out round. Okay. Bracket conf int 1, comma 2. What is the meaning of this? Why it is called round?
It is rounding off 1.85. Sorry, 10.59 to 10.6.
Yeah, it is 9.54 initially. So it becomes 9.54 to 548. So it becomes only the 9.5. Like that, the next one will be the 10.6. This is clear to all of you? Any question?
So what does the set seed command do?
What happened? I cannot follow. Who is saying?
The set seed command. So Sarah wrote the set seed command that we use set the set dot seed 1, 2, 3. What is its function?
I cannot follow.
Sir,
Sorry.
what is the meaning of set dot seed command?
Oh, acha. Yes. Because when you are following the R norm, so it is a random data generation. Okay. And for that reason, you are using the set seed command so that more data can be generated. So it is a set seed for reproducibility. Acha, now you write down Q plot. No. QQ plot. No bracket. Oh no. QQ plot bracket sample data. Enter. What happened? Oh, sorry. QQ norm. QQ NORM. Norm. Bracket sample data. Enter. Okay. This is the quantile plot. Then you write down QQ line. Enter. Okay.
So how will we interpret quantile graphs?
So one is the sample quantile that is based upon your data. Another one is the theoretical quantile. Theoretical quantile means normal distribution. Okay. So to what extent sample distribution is matched with the theoretical distribution, that can be easily understood by this QQ plot. Okay, in doctoral dissertation, most of the time, students are asked this question. Okay, you have used the correlation, you have used the t-test, ANOVA, but have you checked that is your data maintains the quality? Okay. Then you have to tell, yes, I have checked the data quality. So what is the meaning of data quality? Can anybody tell me?
So whether the data is, the sample was normally distributed.
Whether the data satisfied,
Repeatable.
whether the data satisfies the assumption of the statistics that you have used.
So normally in the other software, sir, there is a command that or it shows that whether it is following the Gaussian distribution or not. And if it is not a Gaussian distribution, then it gives the command that you have to use this test or non-parametric test. So is it same, sir?
Yes, yes, definitely. Achha, now you write down Shapiro.test. Then bracket sample data. What you have noted, is it significant?
No, sir.
No. That means your distribution follows the normal distribution. Okay.
So, sir, if this normality test is not significant, then our data follows normal
Yes.
distribution.
If your that is the null hypothesis. That means there is no difference between the sample distribution and the theoretical distribution. Okay. But if it is significant, that means sample distribution is different from the theoretical distribution. Is it clear to all of you? The beauty of the normal probability curve?
So we can say that if it is coming significant, sir, there is a skew in our data.
Maybe.
Yeah, means it is maybe it always
Yeah.
not.
No, it should be. Actually, you have to check. You have to check, that is where skewedness is there. You have to identify. Okay, for example, you write down empty cards $MPG. And before that, you write down QQ norm. Bracket empty cards $MPG. Enter. Okay. Then you write down QQ line. What you have noted, whether all the data are on the line or not.
Some are online, some are not online.
Yes. That means maybe There is a possibility for skewness of the data. Then you write down Shapiro.test. Bracket empty cards $MPG. Enter. Oh, that's good. Though we find that is the some data are not on the QQ line, but still we find there is no significant difference. That means we can apply the parametric statistics for this particular data. Okay. So we have to give maximum priority on the Shapiro Wilks normality test. Okay. So suppose you are interested for doing the principal component analysis, ANOVA like that, it is better to check whether your distribution follows the normal distribution or not. Okay. Any more question?
No, sir.
Okay, now stop share. And if you have any question about your data collection, data design, anything, you can ask me. What is your current status?
Good evening, sir. It's Seema.
Yes, Shima, please.
My status is very bad regarding data collection.
It is a challenge.
So recently I was filing the data on Excel sheet. What I found that all the data are the same, no variation at any item. Dictation type. No error, zero error. All are same.
Maybe there is a lack of rapport. If you maintain the good rapport, that is it. It will not come.
But the problem is this ki, only Saturday is free, and most of the times schools or authorities are saying just leave your papers and the teachers will fill it, and then again the another day you can come and collect it.
No. In that way, you cannot get the good data. And especially the data you are collecting in Uttar Pradesh. People are very much afraid.
So what should I do?
And the people are very much afraid. A lot of uncertainties is there.